Hey everyone, we're going to explore the Holt exponential smoothing method with some population data for low-income countries from 1960 to 2017 today. So go ahead and open up the population underscore low inc data set in RStudio, and you'll also want to make sure that you have the forecast package installed in R. While you're working on that, a little bit on this method. The Holt exponential smoothing method incorporates long-term movements of a time series. We like to use it when the time series does not seem to have seasonal variations, or maybe we've removed those seasonal variations using some other technique first. So the method uses two recursive equations to smooth the series for level and trend. And we're not going to get into the math, so just trust me on this one, and we can circle back to that math later on. But these equations rely on initial values of L1 and T1 and the values of the smoothing parameters of alpha and beta, which we can either choose ourselves or they can be computer generated by optimizing some specific performance measure. A common choice for alpha is 0.20 and a common choice for beta is 0.15. So now that you should have imported your data and made sure you have the forecast package, let's get started with our example. So according to data compiled by the World Bank, the world population increased from 3.03 billion people in 1960 to 7.53 billion people in 2017. This rapid growth is concerning to many individuals and organizations focused on environmental conditions around the world. Growth has accelerated the most in countries classified by the World Bank as low income. And we can explore this growth and make forecasts using the Holt exponential smoothing method. So let's get started. First things first, let's add forecast to our working library. So I'm going to use the library function and forecast. Now it's in and I don't need to worry about the functions within the forecast package not doing what I want them to do. So next we're going to use the TS function, TS time series function to create a new time series object, and we're going to call that object new data. So new data. I'm going to use my assignment arrow, and we're going to use the TS function to create this object. And I called my data, well, I called it my data when I imported it, and I'm going to call on the population variable. And then the very first year in my data is 1960. So I'm going to specify that. The last year in my data set is 2017. You can scroll down in the data pane to make sure that I'm not lying, but I promise it's 2017. And then I'm going to use the frequency attribute to indicate how many time periods are or occur within a year. And in this case, I have annual data. There's only 1 year in a year, so my frequency is going to be set to 1. I'm going to hit enter, and now we see that in our environment pane, we have new data as an object that's been created, and that is our time series object. So now we want to partition the data into a training and a validation or a test set. The training set is what we use to build the model, and the validation set helps us test the model to make sure that it is making reasonable predictions. So the first thing I'm going to do is create my training set. I'm going to call that T data. I'm going to use the window function to help us pull a subset from our new data time series object. So new data, and I want this training data to end at year 2000. Enter, and now we see in the environment pane we have this T-data object, which has 41 values in it ranging from 1960 to year 2000. And now my validation or my testing set is going to be those years beginning in 2001 through the end of my data set. And I'm going to call this vData. And I'm going to use the window function again to take a snapshot from my new data object. And instead of using end, I'm using start and see 2001. So now my validation or my testing data set includes all those observations from 2001 through 2017. And we can see that here in the environment pane, that now vData is a time series object with data from 2001 through 2017. So now we need to specify the type of model or the characteristics of the model we want to use to conduct this analysis. And we can specify this using the ETS function. The ETS function represents the characteristics of error, trend, and seasonality in the model that you want to run. And we use a 3-letter string to denote the error type, the trend type, and the seasonality type. There are more details on the different letters representing different types of conditions in models in the textbook, but in our model, both our error and trend are additive, so they're represented by the letter A. The season type is none. Our data has no seasonality to it. So we represent the seasonality with the letter N. And we want to specify this information and our alpha and beta values to incorporate them into a model when we use this ETS function. So we're going to do this specification. We're going to create an object, HUser. We're going to use that ETS function to specify exactly what we want to, how we want to structure this model. And we're going to be using our testing data, so T-data. And our model is going to be structured with that AAN specification, our additive error, additive trend, and no seasonality is what that 3-letter string represents. And then we also want to add in our values for alpha. We're going to go with 0.2, which is a very common choice. And we're going to specify our value for beta, which we're going to go with 0.15. Again, that's just a very, very common sort of default choice. So this is the approach with user-specified alphas and betas. I'm going to hit enter, and now we're going to see under data, we now have this HUser model. But we can also very similarly specify this model to work using computer-generated parameters. And for that, we're going to create HCMP. And how we use the ETS function is very similar. It's just that we don't specify that alpha and beta value. So we're still interested in our testing data. And our model type is still specified as our AAN. But we don't have to specify alpha and beta for this computer-generated approach. And I'll hit enter. And now we see under data, we have HCMP as well. So now we have both of these models, our computer-generated and our user-specified models. And now we can use the summary function to view the results of each of these models. So first we'll look at our user-specified model, which we called HUser. And I'll just extend this window a little bit, and you can see the results of the model. The smoothing parameters of alpha and beta that we chose are listed, and we can now see the different measures generated by our user-generated model. And we can do the same thing looking at our computer generated model by doing HCMP, which is what we called that computer generated model. And we can compare the results. We see that the smoothing parameters are quite a bit different, and we can see that we have the different measures of comparison between the two models. Kind of offhand, we can see that a lot of the values in the computer generated scenario are quite a bit smaller than in our user generated scenario. And generally we're looking for the smallest values, but sometimes there may be very specific reasons to choose very specific parameters. So we want to make sure that we're not always just assuming the computer generated model is the best. There may be very good reasons to specify your own parameters. So we've now built our model with the testing data set. Yay! Now we want to work with our validation data set to help determine the accuracy of the models we just built. So first, we'll use the length function to find the number of observations in our validation set. So NV is going to be the number of observations in our validation set. And we're going to use the length function on our VData object to determine the length of that vector. So we see that NV has a length of 17. I know you probably figured that out when we set up that validation data set as time series from 2001 to 2017. But it's good to have an object that we can just plug into the code as we go ahead and we start forecasting and making predictions with this data set. So now we want to use the forecast function to create a forecast or prediction value to match each row of the data in the validation set. And we'll do this both with the user specified model as well as the computer generated model. So first with our user specified model, we're going to call this object FUser. Use the forecast function. Maybe I can type. And we are going to forecast using that HUser model. And we're going to set H to NV, which is the length of that validation set. So H basically represents the number of predictions that you want to make. And for us, it's simple. We want to make a prediction to match every row in our testing or validation data set. So we see that has been created in our global environment pane. FUser is now a list of 10, so it has produced something, and we'll do the same thing with the computer generated model. We'll call this one FCMP and use the forecast function on our HCMP model. And again, we want it to make forecasts for each row in that validation data set. So we're setting H to equal NV. Hit enter, and now that object is created. So now that we've created these items, well, we're probably really interested in comparing our forecast results with the actual observations in our data set for these years. So to do this, we can use the accuracy function. And I'll type accuracy. And then we want to compare the results for FUser with our tester validation data set, which was VData. So here we can generally see the validity of the predictions between our given data set and what is predicted based on the model generated with our testing set. And again, we're using the same types of calculated measures, except in R, the validation set is called the test set, MAD is reported as MAE, MSE is the square of RMSE, but MAPE is still MAPE in these models. And knowing that that's how R specifies those measures, well, let me just say that it might come up in your homework, so that's a little heads up. And now we can check the accuracy compared to with our computer generated model with our validation data. And we can compare these measures of accuracy with each other, just keeping in mind that usually the smaller the better. So when you're comparing the MAD, MSE, and MAPE, always keep that in mind. Generally, a smaller measure suggests more precision in your model. And now we can go ahead and use the entire data set, combining both the training and validation sets, to re-implement the preferred model for making forecasts. For this, we'll call this H final, because it's our final Holt model. H Holt final, because it's the final one. And we'll use that Ets function again with our whole data, so our new data set, and specify that model is equal to AAN. We're not specifying the alpha and the beta because by comparing the computer generated and the user specified results, we find that the computer generated result was generally better. So we're just going to specify that the model type is AAN, and we're going to let the computer take the wheel in terms of specifying values for alpha and beta. So now that that's done, we have a functional model that we can use to make population forecasts. Say we wanted to forecast global population in 2018, 2019, and 2020. We'll use the forecast function again. So forecast, and then we're going to have it use that H final model, and we're going to set H to 3 because we want it to forecast the next 3 years. So here we see point forecasts for 2018, 2019, and 2020 in terms of global population. So you can look it up and see if those values match what was actually observed in 2018 and 2019 for these countries classified as low income. But it's pretty interesting stuff, and well, hopefully that'll help you with your homework. Good luck, and keep plugging away at it. You're almost done.